All right, in the last video, we ended with this example where we were looking at a function, f of x equals negative x squared plus 5x minus 3. And we were looking at the graph, or not the graphs, the slopes of various different secant lines, all of which pass through the point on that curve for this graph, or for this function, where x is equal to 1. And then the second point, because remember you need 2 points for a secant line, corresponded to some x value that was getting closer and closer to that 1 for each step in this example. So all we did is we computed the slopes, but we didn't actually look at what these secant lines all looked like. And I want to do that on this next page here. So what we're seeing in red is the curve corresponding to the function that we looked at in that previous example. So that curve is that f of x. And then we found the slopes of 3 different secant lines, and those secant lines are shown here in the green, those green dashed lines, okay? So you can see the points themselves. Notice all 3 secant lines pass through this point here where our x coordinate is 1. So you can kind of see the x-axis down here. So that's 1 f of 1, that's that point. All 3 secant lines pass through that. Where they differ is the second point. So the first example we did passed through the point 2 f of 2, which is off screen, but it's right here. So that's the first dashed line that we found, that first secant line that we found the slope of. And then we tried finding the secant line on the interval 1, 1.5. So that would have passed through these 2 points. And then we found the slope of the secant line passing through the points corresponding to 1 and 1.1. This is actually a typo right here. That should say 1.1 f of 1.1. Okay, so if you notice what's happening to these green dashed lines, as this second end point is brought closer and closer to our left end point for each of those intervals, 1 f of 1. So we have here, and then here, and then they're getting brought closer and closer together. Those green dashed lines are approaching this blue line that I put in here as well. And that blue line is what we call a tangent line. So basically what that blue line is it's the line that just touches the graph of f of x at the point 1 f of 1. So where that left endpoint was for each of those intervals. It just touches that graph, almost like it kind of hits that point and bounces off of it in a sense. That is what's called the tangent line to this graph. And that tangent line, its slope in particular, has a very, very important interpretation. So we're seeing down here where I'm defining tangent line, the slope of that tangent line represents the instantaneous rate of change in our function f of x at that x value, at x equals 1. And remember, that's kind of what we've been working towards this whole time, is how to find an instantaneous rate of change as opposed to just an average rate of change, which really just approximates that instantaneous rate of change. So if we have a method for finding the slope of that tangent line right there, then we will have found that instantaneous rate of change. And in that previous example, that's kind of what we did in part D, okay? We looked at what was happening in each of these approximations as that second end point of our interval got closer and closer to 1. And we thought, in this case, it looks like it's approaching 3. So that slope of that tangent line would have been 3, which means that would be the instantaneous rate of change in this function when x is equal to 1. But really, if you think about what happened here, we were taking a limit of something. So if you see the 2's here, the 1.5's here, the 1.1's here, we're taking a limit as this number that's appearing in 2 places for each of these like slope formula calculations. We're taking the limit as that thing is approaching this 1 right here. So we can rephrase this whole discussion in terms of limits, which is the main reason why we spent all of chapter 1 developing that idea. So that's going to be what we talk about on this page. Now here's a picture of that graph of our function still in red with the tangent line. I've removed the secant lines and I've zoomed in a lot. And that's to point out something else that these tangent lines are really useful for. So if we can find the tangent line to the graph of a function at a particular value, then we know the slope of that tangent line gives us the instantaneous rate of change in our function at the point that we found that tangent line at. But another really, really important property that these tangent lines have is that they are approximation tools for the function itself. Notice when we zoom in to our function, this blue tangent line is very, very close. It looks very, very close to the red curve, which is what f of x's graph looks like. So basically what a tangent line does is it gives us approximations to the actual function itself when we use values of x that are relatively close to whatever number we used here, 1 in this case, okay? So said kind of differently, suppose that I found this tangent line for this function f of x at x equals 1, and I wanted to approximate the value that the actual function f of x took on at, say, x equals 0.8. Well, if I plug 0.8 into my function, it'll take me to this point on the red curve and this point on the blue line, which is so close to the point on the red curve that these are going to have almost identical y values. They're just going to be very, very close. So the tangent line is approximating the curve at that point. That's something else that we use tangent lines for. So here's where we make this idea kind of official and precise. The instantaneous rate of change of a function f at x equals a, which in this case, x was equal to 1, that would have been like the a in that example, is the slope of the tangent line that passes through that point, a f of a, assuming it exists. Remember, limits can fail to exist, so there are going to be cases where this is not something, it doesn't exist. It's given by this, m, which we use for slope in algebra, equals the limit as x approaches a of f of x over f of a minus f of a over x minus a. This is the slope formula for a secant line, but that x value there is being brought closer and closer to that a right there, which is what we saw in the previous example, and we visualized it with the picture showing us that the secant lines we were finding the slope of were approaching the slope of that tangent line. So this is the thing that we use to give us the slope of a tangent line, which can be interpreted as instantaneous rate of change. Now this limit in particular, for any given function, can oftentimes be very difficult to evaluate in this form. And for that reason, it's helpful to put this in a slightly different form. So notice really what we're doing here is we're finding the slope of a secant line over the interval ax. That's where the a and the x come into play there. But remember, the goal is to make this x approach that a right there, so that this interval is getting smaller and smaller and smaller as the right endpoint approaches the left endpoint. One way of making that, thinking of that from a kind of different perspective, is if we set x equal to a plus some number h, which we imagine as being a very small number. So a plus h is how I would write this interval if I make this substitution here. And then if we want this right endpoint to be brought closer and closer to this a right here, then all we need to do is shrink h down to 0, or have h approach 0, because then this right endpoint will be approaching a if that happens. So we can make some substitutions in this formula right here. Remember, x, we're defining it to be a plus h, so anywhere I see an x, I can replace that with an a plus h in that limit. And as x approaches a, we saw here, that's the same thing as h approaching 0. So I would rewrite my limit as the limit as h approaches 0 of this thing here. Okay? The denominator of this quotient can be simplified. I have an a minus a. That leaves me with just that h right there. So this becomes the limit as h approaches 0 of f of a plus h minus f of a all over h. And this thing can be used as an alternative definition for the slope of a tangent line, which is equivalent to the instantaneous rate of change in our function. And this is actually the one that we will use in practice, not really this one. This is going to be the more practical one for computational stuff, okay? So this is what we are running with now. Let's use it, okay? Find the instantaneous rate of change in the function f of x equals x squared plus 5 at x equals 2. So that instantaneous rate of change was defined to be the limit as h approached 0 of f of a plus h. No, in this case, a is 2. So I'm going to write that as 2 plus h minus f of a, which is 2, all over h. Okay? Excuse me. So now what we want to do is figure out what this numerator actually looks like. So this is, again, the limit as h approaches 0 of, I want to take 2 plus h and substitute it in for the x here. So that's going to look like 2 plus h squared plus 5. So there's the function when I plug a 2 plus h into it, minus f of 2. We can do this part in our heads if we want to, but for the sake of this first example, let's write out more of the steps so you see what's going on. 2 gets plugged in for x, so that's 2 squared plus 5, and it's all over h. Our goal here is to try and evaluate this limit. And it's helpful to simplify things as much as possible if we can. So here, 2 squared is 4 plus 5, that's 9. 5 minus 9 would be negative 4. So I'm going to get a negative 4 from all this stuff. And then I'm going to expand this guy here. From algebra, I know exactly what that would look like. 4 plus 4h plus h squared. Okay, now if you're rusty on your algebra, you can go through some steps to get this. You can write 2 plus h times 2 plus h and then use that FOIL method to multiply that out. But this is also a perfect square trinomial, and I know how to compute those just in my head because we learned techniques for that in algebra. I'm not going over all of that right now, so hopefully you remember how that works. So that's what this happens to this expression when I expand that out. We said we would have gotten a negative 4 from the rest of that stuff, all over h. And now I have the limit as h approaches 0. Notice that the 4 and the negative 4 will cancel each other out. So I've got 4h plus h squared over h. Okay? At this point, if I were to try to evaluate this limit directly by taking the limit up into the numerator and denominator separately, my numerator and denominator are both polynomials, and we know that we can use direct substitution to evaluate those types of limits. However, if I did that, I would get a 0 in my numerator and a 0 in my denominator. It's one of those indeterminate forms that we've talked about. Okay? So in this case, I want to simplify this further to see if anything cancels out that will make this limit easier to evaluate. And something does cancel out. It's the h. Now, by this point, hopefully you're not making this mistake. But if you are, it's tempting for some people to just cancel that h with one of these h's up here, which is algebraically invalid. It does not work that way. What you're canceling out is an h in a denominator, which means you're using division. And division does not cancel out something that's part of a sum. So what I would do is factor an h out first. Okay? I have h times something. Then dividing that by h would cancel the original h that I divided by. That's equal to the limit as h approaches 0 of just 4 plus h. At this point, there's no dividing by 0 if I use direct substitution. And this is a continuous function. I can use direct substitution. This would just give me 4. So that instantaneous rate of change in this function at x equals 2 is 4. Now, This step right here, where I factored that h out, you're not going to see me do that again. In the future, what I'm going to do is just say this h cancels with that h and one of these h's, leaving me with 4 plus the other h. And I'll probably go right from this step down to this step, because you really shouldn't need me to show you this. This is very, very basic algebra. And if you don't have a really good handle on your algebra in a calculus course, you're going to have a very, very hard time. The algebra is all over the place in this class. So we need to be able to do stuff like this without having to think through it. I just wanted to do that one time in case you're a little bit rusty. So what we just did is actually, let me come back up here. What we just did is we evaluated the instantaneous rate of change in a function using that limit definition. Now, if I remove that limit for a second, this quotient right here is something that we call a difference quotient. I'm going to write that in, difference quotient. Okay? You're going to be dealing with a lot of these in this chapter. But a difference quotient is something that takes this exact form, f of a plus h minus f of a all over h. And we call it a difference quotient because, as the name implies, it involves a difference between two things and a quotient between two things. So the name is pretty intuitive, I guess. This is our four-step process that we're going to follow for evaluating instantaneous rates of change using these difference quotients, okay? And you may not see me actually go through each of these steps meticulously. This is more just to give you kind of a guide if you're struggling with this. So the first thing you want to do is calculate f of a plus h. We did that up here. So f of 2 plus h, a was 2 in this case. I evaluated it. It's 2 plus h quantity squared plus 5. That's what that's equal to. Okay? Calculate the numerator of the difference quotient. This is the second step. And algebraically manipulate the resulting expression if possible. So this is what our numerator looked like, f of a plus h minus f of a, or in our case, f of 2 plus h minus f of 2. So the second step was evaluating this, which we did, and algebraically manipulating it, which is another way of kind of saying simplify it. Notice some things canceled out. We were able to factor. We were able to do a bunch of stuff to simplify that numerator, okay? Calculate the difference quotient and algebraically manipulate the resulting expression. So that's when we have this thing over h. Really what this third step is talking about is what we did right here. This is the first time I interacted with that denominator. For all these other steps, that h was just along for the ride. But here's where it actually ended up canceling out. So we simplified that quotient using that denominator. At that point, once things have been simplified as much as possible, that's when you want to evaluate that limit. And again, that was the last step that we did. We got it to a point where we could find our limit using direct substitution. And then we did it, okay? So really what I want to do is a handful of examples